Proportions summarize categorical data, and previously we explored the distribution of a sample proportion. Means summarize quantitative data, and they are equally important is the concept of the sampling distribution of a mean. In the previous section, we saw that provided the sample size is large, in the previous section, we saw that provided the sample size was large enough, if you drew repeated random samples of the same size from a population and measured the sample proportion that we call p hat, we get for each sample that the collection of all the sample proportions would pile up to form a normal distribution. Amazingly, the same is true for sample means that we symbolize by X bar. The result is summarized on the next slide and is referred to as the central limit theorem. There are some important parts of the central limit theorem. One has to do with its being normal. In other words, the sample size has to be large for sample means to be normally distributed. The other has to do with the population mean. The population mean of the sampling distribution is same as the population mean itself. And the other has to do with the standard deviation or standard error. And that has a dependency on the sample size. The larger the sample size, the less variability in the sampling distribution for the mean. Specifically, the sampling distribution of the mean, referred to as the standard error, is the population standard deviation divided by the square root of n. Now, it seems reasonable to imitate the process we used for proportions in order to get a confidence interval for a mean. Once again, here's the familiar formula for a proportion. You start with the sample proportion, you add and subtract a critical z-value, and you multiply by the standard error of the proportion. So if we use the results from proportions to model a formula for means, the margin of error term would be z times the standard deviation over the square root of the sample size. The standard deviation of the sampling distribution of the mean is called the standard error, and it's given by, I'm reminding you, this formula, sigma over the square root of n. So why can't life be that easy? Sadly, there are two big problems. One is that the sample size needs to be large in order for the sampling distribution of the mean to be normally distributed. The other is we don't know the population standard deviation, but only the sample standard deviation when we are conducting an experiment. So here's a fascinating little story about a man who made a really big contribution to statistics. His name is Gosset. And working in the late 1800s, Gosset had the job that was envy of many. He was the quality control manager for a Guinness brewery in Dublin, Ireland. He was using just small samples of size 3 and 4, since larger samples would be unhealthy. He noticed that his estimates were off considerably, and this bothered him. He took time off and got a graduate degree in statistics. So he found a way to deal with small samples and the problem of using the sample standard deviation by creating his own model, which he called the t-distribution. So why didn't he name it after himself and call it the Gosset distribution? Well, Guinness carefully guarded their brewing secrets and prohibited any of their employees from publishing anything, even mathematical results. So he published the results using his name, student, or using the name, student, and the distribution is now called the student t distribution. So what are the characteristics of the t distribution? Like the normal distribution is symmetrical, but every time you change the sample size, you change the shape of the curve slightly. There's not just one t distribution, but a different one for each sample size. So to give you an idea, the solid curve is the t distribution for a sample of size 3. And the dash curve is the normal distribution. So as the sample size gets larger, the t distribution gets to look more and more like the normal curve. However, it does not follow the 68, 95, 99% rule. In practice nowadays, everyone uses either a calculator or computer to compute t-values. It's important to remember that, unlike z-scores, t-values depend on the sample size. So when we're using a calculator, we're going to be asked to supply something called a degrees of freedom, which is abbreviated DF. And the definition is the degrees of freedom is 1 less than the sample size. So when the sample size is small, the t-values are large. We are again going to take a technological approach to finding t-values and use an online t-calculator that can be found in StatCrunch in the menu Stat Calculators. So I want to give you an example. We want to establish a 95% confidence interval. Our sample size is 20, and we're going to use the calculator. When it comes to degrees of freedom, we'll enter 19, which is 20 minus 1. The probability will be 0.95, and we'll make sure that the third graph is checked off. So let's see how that works. This is what it looks like. We're going to click between. We want to chop off the middle 95% of the t distribution. So we'll enter 0.95 for the area. We want the t distribution with 19 degrees of freedom, and it reports back that the critical values are 2.093. So that's the value we need in the confidence interval formula. When it comes to evaluating the confidence interval, this is what the formula will look like. It takes the basic form, the sample mean, plus or minus a margin of error. The margin of error is given by the critical t-value provided by the calculator, the sample standard deviation, and the sample size.